The last part of chapter 1 then is 1D, which is velocity time graphs. So we already saw distance time graphs. Now we're looking at velocity time graphs. It's the same thing. So the y-axis should be the velocity of the object, which you remember is the speed, but it is in a certain direction because it's a vector, whereas distance was a scalar. And then time on the x-axis. Now generally, again, the units could be different, but velocity, the standard unit we use for velocity is meters per second, and the standard unit we use for time is in seconds. So velocity time graph, velocity on the y, time on the x, velocity units are meters per second, and the time units are seconds. This one's actually a little bit harder because it has negative values, so we'll discuss the negatives in a second, but this is a really nice simple velocity time graph. Now, the same as what we did for the distance time graph, we just interpret the graph. We're not drawing it, we've already drawn it or the exam gave it to us, but we have to discuss what's going on in each stage. Now, if we look, we have a stage number 1, or A, where it starts at 0 velocity, so it starts from rest at 0 speed. It's then increasing its velocity, so time is started, it's increasing its velocity in a specific time. So let's add some values on. Let's say that that velocity that it reaches here is 6 meters per second, and it takes a time of 5 seconds to get there. Alright, so the first leg of this journey, the speed goes from 0 to 6 meters per second in a time of 5 seconds. So they're increasing speed. Now we know already that increasing speed is acceleration. We just did that in the previous chapter. If something's speed changes, then it is accelerating. Okay? This one is specifically increasing its speed, so it's accelerating in a positive way. Now, what happens here, it's a flat line. Remember, the slope of a graph, the steepness of a graph is the gradient. And the gradient of a motion time graph can tell us something, and we can find new values from the gradient. So this one is a steep line, which means the velocity is increasing, and which we just said means that it's accelerating. This section, like on the distance time, is horizontal, it's flat. That means it has a slope or a gradient of 0. So the velocity stays constant at 6. So if you get a horizontal flat line in a velocity time graph, then the velocity is constant, which means it doesn't mean it's not moving. It is moving because it's at 6 meters, it's traveling at 6 meters per second. So it's definitely moving, but it's moving with a constant speed. Okay, so velocity doesn't change, which means that it's not accelerating. It's traveling with constant velocity, 6 meters per second, so it is moving, it's constant speed, constant velocity, but it's not accelerating because we said acceleration was a changing speed. So here, it's increasing its speed, which means it is accelerating in a certain time. Here, it's constant velocity, it's traveling at constant speed, but it's not accelerating because its speed is not changing. And then the last leg, so let's say that happens it gets to 15 seconds, so that took 10 seconds of traveling at constant speed. And then from 6, it reduces its speed, or it decreases its velocity from 6 to 0. So it comes back to rest. Now this is velocity, so it's traveling at a constant 6 forwards, let's say, and then it reduces its speed back to 0, and then it comes to a stop. Let's say that happens at 20 seconds, so 5 seconds later. Okay? This one is decreasing speed. Now, that's not an acceleration, or it is acceleration, but it's actually a deceleration because it's slowing down. Alright, so deceleration in this case because it's slowing down. So speeding up in the first section is an acceleration. Changing speed positively, speeding up is acceleration. Constant speed, 0 acceleration, and then decreasing speed, still moving forward. Okay, this is all happening in the positive section of the graph. This is positive numbers, positive time. Okay, all of this happens in the positive, which means it's always moving forward. It's increasing its speed forwards. It's traveling at constant speed forwards. It then slows down back to 0 to a stop, but still forwards. It still has to travel some distance. When you put the brakes on in a car, and you're traveling at 6 meters per second, and then you put your brakes on and you come to 0, you come to a stop in 5 seconds, you still have to move forwards. Alright, so all of this journey, section A, section B, and section C, are all happening forwards. And how do I know it's forwards? Because all of it is in the positive section of the graph. There is no negative in this graph. I didn't draw any negative, so that means all of this is forwards. A lot of people think because it's slowing down, it's decelerating, that's negative, and it's not. Okay, it's still moving forward, or it's moving backwards. They think that this part here is moving backwards. It's just slowing down, but forwards. And I know that because it's all in the positive. Now, before I show you a more difficult graph with negative values, what can we find from a velocity time graph? We've just said that I even use this graph to say, oh, it must be accelerating here because it's changing speed. It's obviously not accelerating here because it's not changing speed, so constant speed is no acceleration, and it's decelerating here because it's changing its speed but it's slowing down, so it's reducing its speed. So acceleration, no acceleration, deceleration, and that is all based on the gradient of the graph. So if I find the gradient again on this one, remember we have to do a triangle on these sections here. The gradient here is the rise divided by the run. So the gradient there would be the change in speed, which is 6, divided by the change in time, which is 5, and that would tell me the acceleration of the object. So the gradient of a velocity time graph, the gradient of a velocity time graph is the acceleration of the object. All right? This is a forwards acceleration speeding up. This gradient is 0, it's flat, there's no gradient, so acceleration is 0, constant velocity, and this one is a deceleration, so it's slowing down, still forwards. So this one would be 6, again divided by 5, but it would be negative because it's slowing down. All moving forwards. Now the last thing that we need to consider is a graph that's slightly more difficult because it has negative values of velocity. Now, if you have, look, if we start here, we start at actually, we're going 2, 4, 6, 8, 10, so it goes up in 2s, and we start at a velocity of minus 12. And the car travels at minus 12 for just under 4 seconds. Now, minus 12 velocity doesn't mean that it has negative, it has less than 0 velocity, okay? It's not like money in a bank. If you go into the negative, you have less than nothing. What this means is minus 12 velocity, it's still traveling at 12 meters per second. It's very fast. It still has a speed, but it's going the other direction. So negative in the velocity time graph is in one direction, usually backwards, okay? And the positive section in a velocity time graph, so anything above 0, any positive value of velocity is in the other direction. So positive and negative on a velocity time graph only represents forwards and backwards. It's only the direction, okay? All of this happens in the positive. So all of this, speeding up, slowing down, all forwards, okay? Anything that happens in the negative means it's happening in the opposite direction. What happens here? We have a constant velocity of minus 12 for 4 seconds. Because it's a flat line, it means there is no acceleration, okay? So it's not accelerating, it's traveling at a constant speed of 12 meters per second, but that way. So it's traveling along the road for 4 seconds at 12 meters per second that way. Then what it does, it goes from 12 to 0. Now again, a lot of students will think, oh, this one is increasing, so it's an acceleration, okay, because it's an increase on the graph. No, it's coming from 12 to 0, still in the negative section, so it was traveling at 12 meters per second, constant velocity, no acceleration, this way, in 4 seconds, then it slows down, which means it decelerates, still in the negative section, so it's slowing down this way, then it comes to 0 velocity, which means it stops, and then its velocity increases again to 10, 12, 14, 16, 18 meters per second. But it's now in the positive. So it stops, 12 meters per second, slows down this way, stops, and now it increases from 0 to 18 meters per second, but in the opposite direction because it's now crossed into the positive side of the graph, so it now accelerates this direction. So it was constant speed, deceleration, slowing down this way, turned around at 0 and immediately accelerates this way in the positive section from 0 to 18 meters per second. So that is speeding up, but in the opposite direction. Then again it reaches 18 and it travels still in the forwards or other direction at 18 meters per second, and again it slows down here. It's slowing down from 18 to 0, so it comes to a stop, but this section here is all slowing down in that direction. So anything in the negative is happening in that direction, and then anything in the positive, speeding up, constant speed, slowing down, all happens in the opposite direction. So positive and negative on a graph is purely direction. It doesn't mean it's slowing down or speeding up if it goes up or down. It's only direction, because this is speeding up, this is constant speed, and this is slowing down in that direction. This is constant speed, and this is slowing down from 12 to 0 in this direction. There is one more thing we can take from a graph. So far we've had two graphs, distance time graph and now velocity time graph, and we said we can find the gradient of both of those graphs. The gradient of the distance time graph was speed. Speed equals distance divided by time, so the gradient of a distance time graph is speed. The gradient of a velocity time graph, which is velocity or change in velocity divided by time, which we know is acceleration. So the gradient of a velocity time graph is acceleration. But there is one more thing we can find from these graphs, and that is called the area underneath the line. Now, if you want to find the area, this shape for the constant line, the horizontal part, if we make a shape, it's actually a rectangle. Now, if I want to find the area of a rectangle, then I do the length times the width, or in this case, the height. The height of this is 6. It's 0 to 6, so the height of my rectangle is 6. The length goes from 5 to 15, so the length is 10. If I would like to find the area of this rectangle, 6 times 10 is 60. But what does that value represent? Well, I just did the velocity, 6, multiplied by the time, 10. Velocity times time, if you remember from this equation, change in velocity multiplied by time gives you, sorry, not this equation, I did the velocity times the time. Speed times time is distance. So in the velocity time graph, which is here, if I find the area underneath the graph, that's the change in velocity times the time. The change in velocity times the time is the distance traveled. So if I want to find the distance traveled by this car or by an object from the velocity time graph, all I have to do is find the area underneath the line. So in this case, the distance traveled by this object from 5 seconds to 15 seconds at a speed of 6. The height of this rectangle is 6. The length of the rectangle is 10 seconds. 10 times 6 is 60. Therefore, the distance equals 60 meters. Now, only meters if the units of speed are meters per second and the time is in seconds, okay? If it was kilometers and hours, then the distance would be in kilometers. If it was miles per hour and hours, then it would be miles, all right? So the distance, the unit for the distance depends on what the units are for the graph. Mine are meters per second and seconds, so therefore the distance traveled, the area underneath the graph is in meters. Okay, this one was easy because it was a rectangle. So the area underneath the graph, if it's a rectangle, is just the length times the height, which is easy if it's flat. But what about, let's take this area here. What about this area here? So from 0 to 18, let's call this section A, section B, in fact, yeah, we'll do section C, section D, and section E. So A, constant velocity, 12 meters per second that way. B, slowing down from 12 to 0, still that way. C, I'm now in the positive. I turn around and I go from 0 to 18. So I accelerate the opposite direction because I'm now in the positive from 0 to 18 that way. D, constant velocity that way. So I'm still in the positive, meaning I'm still going this way. Constant velocity, 0 acceleration. And E, remember I'm coming from 18 back to 0, so I'm decelerating but I'm still in the positive, so I'm still going that way. Now, if I say to you, or the exam question asks, what is, or calculate the distance traveled by this car from 6 seconds to 9 seconds, or for part C on the graph, all right? So we'd find it. So let's have a look. 6 seconds starts there, and it goes, the section C is to there. Now this, the area underneath this line where it accelerated from 0 to 18, that direction, that is a triangle, not a rectangle. It's just one extra step. If you have a rectangle and you want to find the area underneath the graph, you do the height times the length, and that's the distance. If you want to find the area underneath the line, but it's changing, it's a triangle, then you do the same thing. So we're going to find the height of this triangle to find the area underneath, which is the distance traveled, okay, just for this section, because if they wanted the whole distance traveled in that direction, we'd have to find the whole area, and we'd split it up into a triangle, a rectangle, and a triangle. So we do 3 different areas and add them. I can do that in a second. But we go from 6 to 9, so that's 3 on the, let me zoom in so you can see that. So that one is 3 on the base, so the area of a triangle is base times height, and then we divide it by 2. So base is 3, from 0 to 18, meaning the height is 18. If we times them together, 18 times 3, we've got 54. So 18 times 3 is 54, but because it's a triangle, we have to divide it by 2. So if it were a rectangle, it would be the base times the height, but because it's a triangle, it's just half of that. So 54 divided by 2 is 27, okay? So you have a distance traveled for just this section of 27 meters. Now, if they said, what is the distance traveled for section C and D? So from 6 seconds all the way to 10, 11, 12, 13 seconds. Now, I did the triangle, I split it up into triangle and rectangle. I found the area of the triangle, which was 27 meters. I now need to find the area underneath the line for this rectangle. I already have the height, it's 18, because it's traveling at constant velocity 18. I have the height. The base goes from 9 to 13, which means the base is 4. So if I take 4 for my base, I'm looking for this area of the whole rectangle there. 18 multiplied by 4, that's 40, is 72. So 72 meters. So 18 multiplied by 4, 72 meters just for section D. But if they said for the whole section C and D, or from 6 seconds all the way to 13 seconds, then I would do 72 plus my 27, which takes me to 99 meters. Okay, so total distance traveled for more than one section. You have to find the areas separately and then add them together. Okay, so quick summary, velocity time graphs. We've had a look at a couple. We can just talk about them, constant velocity. If they're in positive and negative, it means direction changes. If they are sloped increase, then it means they're accelerating, speeding up. Even if they were coming down here, so if we went down here like this, then it would be accelerating from 0 to 12, let's say, accelerating, but that direction, speeding up in that direction. This one is speeding up in the other direction because it's in the positive. So the gradient of a velocity time graph is the acceleration. So gradient of a velocity time is acceleration, but also the area underneath the velocity time graph is distance traveled. So they're the things we can find from the velocity time graph. And that's chapter 1 from A to D.